Ladies and gentlemen, welcome to our chapter 5. In this chapter we are covering structures associated with crustal shortening, and this chapter consists of two parts. In the first part, this is this video, we are going to talk about structures that form typically in the brittle ductile transition. In the second part we will cover folds and folding. Both of these structures are typically associated with tectonic settings of convergence. That means horizontal crustal shortening, such as Andean type plate margins, where during subduction the overriding plate will undergo crustal shortening. This setting is normally then followed by continent-continent collision, and also here of course we have horizontal convergence, which typically is associated with crustal thickening. The structures that are associated with these settings are, of course, folds, and folds require, of course, temperatures that allow ductile deformation to take place. In the brittle field, we would form fold structures that indicate horizontal shortening, such as reverse or thrust folds, or also oblique slip folds, where we have a thrust or a reverse fold component. There are three important structures that form in the brittle and semi-ductile field. That means in the brittle ductile transition. These would be flat ramp structures, also called fault bend folds, imbricate fans, and duplex structures. Let's start with the duplex structures. Here we see how a duplex structure would look like. We see individual thrust slices that form horses, as we call them, on top of a fold that is developed underneath them, which often is called a decollement. We see the decollement here. It underlies these horse structures and then forms a ramp cutting through a layer on the bottom and continuing as a flat fold further on top. The individual horses that we see here are separated by individual thrusts, and these thrusts we call ramps. Also, this part here of the decollement would be one of these ramps. Ramps typically cross-cut harder and more competent layers. So this layer that we would see here at the bottom would consist of fairly competent brittle material. The ramps and flats are necessary part of the duplex structures, and we always would find duplex structures covered by a major upper thrust sheet that we see in white color here on the top. The interior of the duplex, that means the part that is formed by the ramps and by the horses, is bound on all sides by tectonic contacts. This is a part of the definition of a duplex structures, individual thrust slices. Let's now discuss how a duplex structure actually evolves over time and how we end up with these stacked horses in the duplex structure. We see here an earlier stage, a upper glide horizon, where a thrust sheet on the top is sliding over a ramp and on top of a stack of brittle layers. This would be a major thrust sheet here on the top. Let's assume that at some stage the critical shear stress along the ramp increases so that it becomes stuck, that no more tectonic slip is possible along that ramp. This would create a stress concentration in this area, and it might lead to the activation of a new ramp further along the brittle layer here at the bottom. So we see here the lower slip horizon would be extended laterally, and a new thrust, a new ramp may form further into the tectonic transport direction of the major thrust sheet. If that happens, this thrust sheet could be activated, but it would require that this section of the brittle lower layer would have to slide up the ramp and form some form of folds. We see here these kink folds are forming while this segment is overriding its footwall along the newly created ramp. Then we have a new glide horizon that no longer makes use of the previous ramp. It makes use of the new ramp, and it ends at the top of the brittle layer, where it then would merge with the upper glide horizon, similar as in the stage that we have seen before. Now let's assume that also this newly created ramp becomes inactive because of increasing shear stresses, and the ramp is no longer suitable as a slip horizon for the hanging wall units, which includes the first horse that we have formed here. The same as before might happen. We form a new ramp further along the brittle layer in the footwall, and that will activate a extension of the lower slip horizon that then will facilitate the formation of the next horse, because also this segment here needs to override its footwall, and it will become bent and folded as the first horse before. Then of course the process can be repeated. We increase the critical shear stress along the ramp, it becomes no longer usable, and a new ramp has to form. This is the way how duplex structures propagate in the direction of the tectonic transport, and new horses form one after another. But why is it actually that these ramps become inactive? Why does the critical shear stress increase and might exceed the stress that is available for tectonic shortening? We can learn from the Mohr stress diagram why that happens. Let's assume we have an active ramp that is a existing fracture, and that the stresses that are available, that means sigma 1 and sigma 2, are of such a magnitude that we can keep such a ramp active. Let's assume this plane orientation that we see here represents the ramp as we see it here in the upper diagram. We would see that at given stress conditions of sigma 3, confining stress of about 13 megapascals, and a sigma 1 of perhaps 69 megapascals, we just reach the envelope of sliding friction. And that means that the critical shear stress is achieved and the normal stress is not too large in order to slide along that ramp, which would be this ramp here. The point is, as soon as we start moving material up the ramp, we are increasing the thickness of material on top of this ramp. And as soon as we are doing that, we increase the normal stress. If we increase the normal stress in such a situation, we would move the Mohr circle a little bit further to the right hand side. That would mean that the confining stress increases, and also the normal stress acting onto our ramp would increase, and at given stress conditions that would shift the Mohr circle to the right hand side of the Mohr stress diagram. We see that represented here by the Mohr circle in the dashed lines, and when you look here at the fold plane that we see here, it is now uncritical. We see the available normal stress and shear stress are not intersecting the envelope of sliding friction, and that means displacement along that fold is no longer possible. Now there are ways out of that. Of course, if tectonic transport gets stuck and stresses are no longer released by tectonic displacement, differential stresses might increase. Let's see how we can describe that in the Mohr stress diagram. We see here our Mohr circle representing the situation when the ramp structure is stuck. We have a confining stress of perhaps around 23, 24 megapascals. Initially we have a sigma 1 that might range at around 80 megapascals. Under these conditions, as we have seen, we cannot use the ramp for further tectonic transport, but stress increase might increase sigma 1. And we see here when our Mohr circle grows to an extent that it eventually becomes critical again, we will have a sigma 1 of around 100 megapascals in this example. That would represent a differential stress of about 76 megapascals. So here we see an increase of the differential stress to 76 megapascals would be sufficient to keep this ramp active and to continue transporting the hanging wall along the ramp onto the upper slip horizon. However, that is not leading to the formation of duplex structures. Duplex structures require that there are more and more horses formed by propagation of new ramp structures further down along the lower brittle layer. And here we see how that might play out in the Mohr stress diagram. In a position where we could form a new ramp, such as here, the overburden is smaller, and that means that our confining stress, our sigma 3, is smaller than in the area of the previously created ramp. That would mean that our confining stress would be the same like at the beginning of the evolution of the Mohr circle. In this example, just under 15 megapascals. If that is our confining stress, we would have to increase sigma 1 to a value of about 81 or 82 megapascals, and that would be sufficient to form this new ramp, because now we are intersecting here with the Coulomb failure envelope at a fracture orientation that is identical to our initial ramp. Once this ramp has formed, the differential stress would drop to a value that is sufficient to intersect the envelope of sliding friction. And in this example, we simply maintain the confining stress of 13 megapascals. Then we drop down to the Mohr circle that we have seen initially 2 slides further up. We also see that the creation of this ramp requires a smaller differential stress than the 76 megapascals that were necessary to keep the earlier ramp tectonically active. This small difference can be the reason why it is easier to create a new ramp and accordingly a new horse rather than keep an earlier ramp active. And as soon as we start uplifting this segment and form the new horse, we will find that again the shear stress along this new ramp will increase and a new ramp will form further down along the brittle layer, as we have seen in previous slides. These are the reasons why duplex structures contain more than one horse and why the duplex structures will propagate always downwards along the brittle competent footwall layer. The next typical feature that we find in the brittle ductile transition are flat ramp structures, which are also often referred to as fault bend folds. On the image here we see a flat ramp structure from the Cape Fault Belt in South Africa, and of course it contains the important brittle features that would be a ramp structure that connects an upper flat and a lower flat fault. The lower flat fault is hidden here behind this bush, but in the field you easily can see it. The geometry of this structure would indicate a hanging wall transport to the right. Schematically, a flat ramp structure consists of more than the ramp and the flat falls. We find schematically here a trailing syncline, a trailing anticline, and the counterparts here of the leading anticline and the leading syncline. That means a flat ramp structure, of course, is a combination of ductile features and brittle features of tectonic displacement. Coming back to our natural example, we could here associate the leading syncline with this fold. The leading anticline would be here, and further to the left we would find the trailing anticline and the trailing syncline. Let's see how flat ramp structures evolve. Let's start with a sequence of layers. Some are more brittle, some are perhaps a little bit more ductile, so different competence in different layers. And in order to keep track of what is happening, let's observe 3 different marker points, the red, the yellow and the blue one. If we start laterally shortening such a sequence of layers, we might eventually form a brittle fold, a ramp structure at about 30 degrees with sigma 1, and we assume in horizontal shortening that also sigma 1 is oriented horizontally, sigma 3 would be vertical. Let's see what happens if we start tectonically using this ramp structure. We see here that instantly the trailing syncline and the trailing anticline form, and also the leading syncline and anticline are forming here in the upper part on at the beginning of the upper flat fold structure. We see that here our marker points are still in a similar position as in the pre-kinematic stage. We see here the red marker is still above the lower flat. The yellow marker point has started climbing up the ramp, and the blue marker point is still on the left hand side of the leading anticline. Let's see what happens in the next stage if we keep transporting material up the ramp. We see now our red marker point is starting to climb up the ramp. The yellow marker point is between the trailing anticline and the leading anticline, and the blue marker point is between the leading anticline and the leading syncline. That means that material starts moving through these fold structures, and that means that all material that is transported up the ramp is in fact folded repeatedly. We also see that the structure itself increases in height, and it increases in height to such an extent until the layer that in the first stage was continuous actually has overridden itself along the ramp. This is achieved here in this example. Once we see here that all our marker points have been transported onto the upper flat, the flat ramp structure cannot grow further vertically. In this stage here we see that the red point has just arrived at this place. The yellow marker point is now beyond the leading anticline, and the blue marker point has also made some progress and is moving from the leading anticline towards the leading syncline. Here we see again our image from the Cape Fold Belt, and let's put the schematic illustration next to it. You see there are quite some similarities. Obviously the schematic sketch here is simplified and shows more clearly the important parts of a flat ramp structure with the trailing syncline and anticline and the leading counterparts, and of course the flat and the ramp structures. But I think we still can recognize these features again in our natural example here on the left hand side. The third structure we want to discuss are imbricate fans. Imbricate fans have similarities with flat ramp structures and also with duplex structures, but they also have some important differences. Again, we are starting with a sequence of horizontal layers that undergo horizontal shortening. We see here the shortening direction, and we assume in such a situation that also sigma 1 is horizontal and sigma 3 is vertical. In such a situation, we might form again cross-cutting thrusts, because thrusts oriented at a dip angle of about 30 degrees are the preferred direction in which contractional faults would form. We see here that process already has started. We have formed a so-called blind thrust, and in contrast to the flat ramp structures or the duplex structures that we have seen before, there is no upper flat thrust or no covering thrust plane in this case. That is why we call these ramps blind thrusts. They do not continue into an upper flat fault structure. What we see here is again that something like a trailing syncline and a trailing anticline, as well as a leading anticline and a leading syncline, has formed, but we do not see that this material is transported further in the shear direction onto the footwall. Instead, what we see is the propagation of the structure along a new incipient ramp, which becomes the next blind thrust. And we see this stage here in our second sketch. We see that here the first blind thrust has kinked a little bit further, the fault plane has been steepened up, and we see that the first set of folds is undergoing further tightening. At the same time, we see here in the second fold set of the imbricate fan a similar evolution as we have seen here in stage 1. Again, this ramp here is a blind thrust. It does not continue further, and in the next stage we are activating a further blind thrust further in the direction of tectonic transport. Here we see the next stage of the evolution of our imbricate fan, consisting of 3 blind thrusts and the sets of folds that have developed on top of them. What is remarkable is that the oldest blind thrust now is the steepest. The second blind thrust also has seen some steepening. The third one is still in its original orientation of about 30 degrees dip angle, but if you would continue the evolution, you might also steepen up the third blind thrust when a further ramp would form and a further set of folds would develop in this imbricate fan. You might ask the question, why do we find these several generations of blind thrusts forming? Why do they become inactive, and why does the imbricate fan propagate? We have seen a similar feature in duplex structures, and the mechanical reason why we propagate an imbricate fan is very similar like the answer that we found for duplex structures. When we start moving material up such a ramp, we will increase the amount of material on top of the blind thrust, and that will increase the normal stress. With increasing normal stress, the critical shear stress increases, and it might exceed the stresses that are available, and this will lead to the formation of a new ramp, which is mechanically easier than keeping the blind thrust alive. In addition, in imbricate fans, we do not have the horizontal continuation of an upper thrust sheet. In addition to these reasons, we will see that the formation of a new blind thrust and the movement of material along this new blind thrust will steepen up the earlier blind thrust that has formed in stage 1. As soon as we steepen up these earlier blind thrust, tectonic displacement along them will become more and more difficult, because we are rotating them out of the preferred 30 degrees angle with respect to sigma 1. they will become more and more vertical and therefore increasingly perpendicular to sigma 1, which lowers the shear stress that can be resolved and increase the proportion of normal stress acting on these earlier blind thrusts. This is detrimental to tectonic transport, where we want to have a high shear stress component and a relatively low normal stress component. So here we have the three structures that we have discussed together: the flat ramp structure, the imbricate fans, and the duplex structures. What do these structures have in common? What distinguishes them from each other? There are a couple of similarities. Of course, they all are typically developed in the brittle ductile transition because all of them have brittle components. The ramps, the blind thrusts that we see here. We see here the lower flat and the upper flat. The difference between the flat ramp structure and the duplex structure is that the flat ramp structure does not propagate laterally in the direction of the tectonic transport. We might keep the ramp active for quite some time and move a lot of material on top of the footwall during the progressive tectonic transport. In the duplex structure, we keep the ramps active for only short time before the structure propagates further into the direction of tectonic transport. In the imbricate fan, we form only blind thrusts. That means these thrusts are not continuing into an upper thrust sheet that would allow a large amount of tectonic transport. That forces the imbricate fan to propagate by the formation of new ramps into the direction of tectonic transport, and the steepening of the older ramps will prevent further tectonic transport along these earlier structures. Thank you very much. In the second part of this chapter 5, we are going to talk about folds and folding.